back here and welcome you all to the last day of our summer school. It's hard to believe that it's already the last day. Time went by way too quickly, and I must say that you have been a fantastic crowd of students, and I think we very much enjoy to have you here as our guests, and I also hope that you enjoyed the school. I have a few final announcements for the last day. So first of all, please take your posters off, and I think the coffee break is a good opportunity to go and take your poster off. Then of course we have our friendly evaluation form for the school, and you're kindly asked to give us some feedback on what was good, what was not so good, what you would like to keep, and what are your suggestions for improvements for next time. So even if you may not attend next time, the next crowd of people would probably appreciate that if you help us making that school better. Then there is the certificate that all of you can pick up, where we certify that you have been taking the school, and you can get your certificate at the conference office, anytime today. After the last practical, those of you who have borrowed computers from us, please return them. I know that this is a nice thing to keep, but we would appreciate if you could get our computers back. And of course, after the last practical, don't forget, we will have a social event. We will barbecue outside of that place here. And so for those of you who don't rush out, there is a little opportunity to stay together, have a good time, and let the school fade out. Okay? And with that, I will come to the second last lecture of the summer school, and it is on vibrational spectroscopy. And what I want to stress here, and I think I stressed it again in the beginning, when you do spectroscopy, it's always important to get yourself oriented on the photon energy and molecular phenomena that are associated with it. And throughout the school, we have led you through many orders of magnitude of photon energy. And you have heard about Max spectroscopy from Eckhart Bill, X-ray absorption spectroscopy from Serena Napier, UV visible and MCD spectroscopy from Felix Dubček. You have heard about EPR and Endor spectroscopy from Maurice van Gastel and Nick Cox. And so what is left to do is to cover the infrared region of the spectrum, and that corresponds to IR, Raman, and in particular resonance Raman spectroscopy that deals with molecular vibrations. So what we want to do today is I will first give you an introduction and motivate the use of vibrational spectroscopy. We will then look at a little detail at the nature of molecular vibrations. We will look at the physical origin of IR, Raman, and resonance Raman intensities. We will then look at applications in inorganic and bioinorganic chemistry, and if there is time left, which I actually doubt, we can also talk a little bit about experimental techniques. So first of all, why would you want to do vibrational spectroscopy? So first of all, vibrational spectroscopy contains structural information. All of these vibrational techniques contain structural information. And I'm very sure that all of you who have studied chemistry are very familiar with identifying characteristic group vibrations. So we all know what a carbonyl group, for example, or a carboxylate group does in the IR spectrum. So there are fingerprint vibrations. If you want to prove the nature of a vibration or the involvement of a given group in a vibration, then you can employ isotope shift. We'll look at it in a little bit later. You get much more detailed information if you perform normal coordinate analysis, and of course you can detect functional groups. Very importantly, it is not just vibrational information or structural information. There also is a lot of electronic information in the vibrational spectrum, and this is nowhere more clearly exposed as in resonance Raman spectroscopy. We will look at that in some detail later, and you have heard yesterday from Felix Dubček how MCD spectroscopy is such a powerful link between the magnetic properties of the ground state and the excited states that you probe in absorption spectroscopy, and in a similar way resonance Raman spectroscopy is a superbly powerful link between optical spectroscopy and vibrational spectroscopy. So you can use resonance Raman spectroscopy to identify electronic transitions. Then there is the subject of resonance Raman excitation profiles, from which you can deduce very detailed information on excited state structures, and you can get a lot of insight into the bonding, the properties of the chemical bonds in the electronic ground state. You can, as you can with most spectroscopies, do it in a time-resolved fashion, so there is mechanistic information, chemical information that you can deduce from vibrational spectroscopy. For example, you can trap short-lived intermediates by freeze quench techniques or stop flow techniques or continuous flow techniques. And if you do that, that is a very powerful way to identify reaction intermediates and characterize them. Last but not least, vibrational spectroscopy is nicely complementary to the array of other techniques that you have heard about. So vibrational spectra you can always record, even if your ground state is not magnetic. And of course, if you're an organic chemist, then you ask, what is that person talking about? My molecules are never magnetic. But in inorganic chemistry, they're mostly magnetic, and those that are not, that cannot be probed by EPR or MCD spectroscopy, you can nicely probe by vibrational spectroscopy. It is much higher resolution than absorption or circular dichroism spectroscopy, and importantly, vibrational spectroscopy is not limited to certain isotopes as Mossbauer spectroscopy is. So it fills a nice niche, an important niche in the array of spectroscopic tools, and it's good to be familiar with what you can do with it. Now, experimentally, IR versus Raman spectroscopy is really very, very different. The IR experiment, in principle, is nothing else but an absorption spectroscopic experiment using IR light sources. So in principle, it is a dead standard absorption experiment where you have an infrared light source, you have a reference and a sample cuvette, you have an IR detector, and then you have a Lambert-Beer law that relates the absorption to the molecular extinction coefficient for the vibrational transition. So from that perspective, it is just the same as absorption spectroscopy, just with lower energy radiation. The Raman experiment, on the other hand, is interesting because you probe molecular vibrations by using optical light. So here you have a laser source that is operating not in the infrared, but is operating in the visible or in the near infrared. So if you have a resonance Raman spectroscopic experiment, you have a laser source with variable frequency, and you need variable frequency to excite into an absorption band. But many of the commercial Raman spectrometers, they use a fixed frequency laser that is operating somewhere in the near infrared, so very many of them have neodymium YAG at like something over 1,000 nanometers radiation. And so that light has hit the sample, and you don't detect absorption, you detect the scattered light. And it was a fairly spectacular experiment when it was shown finally that the scattered light does not only contain the frequency that you excite with, but that there are side bands. So there are vibrational frequencies, or there are frequencies scattered that are different from the excitation frequency. So the portion of the light that is scattered at the same frequency, and that is the vast majority of it, that is called the Rayleigh scattering, and so therefore there's a very intense Rayleigh line. And then you have those scattered frequencies that are lower in frequency than the excitation frequency. Those are called Stokes lines. And their deviation, their difference, from the Rayleigh line, that is called the Raman shift. So that was called after Sir Raman, who discovered the effect. And so the difference from the Rayleigh line, of these peaks from the Rayleigh line, that is the vibrational information that you have. If you go to the opposite side, where you have higher frequency than the excitation frequency, those are called anti-Stokes lines. Now the nice thing is the scattered radiation you can detect with a visible detector. So very often these are like CCD cameras, and they're superbly sensitive. So all of the optical components work best when the light is in the visible range. And so here you have superbly sensitive instruments that you have right now. Yeah? The scattering actually depends on the force power of the excitation frequency. Now, as I'm sure you have heard in your lectures on spectroscopy in university, IR and Raman spectroscopy are complementary, and you have selection rules that tell you that a vibration is active, like for a molecule that has center of inversion, at least that an IR active vibration needs to be ungerade, and Raman vibration to be active in the Raman spectrum needs to be gerade. If you have low symmetry, that doesn't apply. And this plot here, this spectrum here on a simple compound, methyl thioacetate, simply shows, nicely shows how you have complementary information, and those peaks that you observe in the Raman, and they're there in the infrared and vice versa. So that is nice. Now, if you apply, many of you are studying proteins or large molecules, and obviously there are many, many vibrational peaks there. So if you look at a protein, for example, that has thousands of atoms, obviously you also get thousands of peaks in the IR and Raman spectra, and that is impossible to study in detail. Over the years it has been worked out, and just empirically so, that you get Raman and IR spectra that are globally sensitive to secondary structure elements like beta sheets and alpha helices and these things, complementary to how circular dichroism is used in biochemistry. That is perhaps, at least in my mind, one of the less interesting applications of vibrational spectroscopy, and the question is now how, for a large molecule, do you obtain, or do you like extract the interesting information? And it is here where resonance Raman spectroscopy really excels, because what resonance Raman spectroscopy sees are vibrations that are coupled to a chromophore. So for example, if you have a chromophoric group here that absorbs somewhere in the visible in that macromolecule, you can tune your laser into an absorption band, and hemes are a very prominent example in that respect, and you detect only vibrations that are happening in and around the heme group. So that is a fantastically sensitive probe of the vibrational fingerprint of given chromophoric groups. If you have several chromophoric groups that have isolated absorption bands, then of course you can selectively enhance vibrations of one or the other, so you have a super sensitive probe into specific regions of a large molecule. You cannot do that with standard Raman spectroscopy, and also not with standard IR spectroscopy that always see all of the vibrations of everything that is in your cuvette. In terms of proteins, you sometimes are lucky, and there are windows where protein, like spectral windows where the protein doesn't absorb, and then you can use highly sensitive difference FTIR spectroscopy to detect changes in vibrations. But whenever your molecules get larger, your method of choice really is resonance Raman spectroscopy. Now, with that as motivation, I think we go way, way back and look at the physical principles that govern vibrational spectra. And so here I want to remind you on the first lecture that I've given you, where I've talked about the Born-Oppenheimer approximation and how it allows us to separate the full molecular Schrödinger equation into two equations, one for the electrons and one for the nuclei. And I told you, at least I noted in passing, that the solution of the electronic Schrödinger equation at fixed nuclear geometry provides then the playground or the background, the effective potential in which the nuclei move. And we also talked about potential energy surfaces. And so what you see here is the potential energy surface of a diatomic molecule, and you see by every position of these dots, so there is the x-axis is some nuclear coordinate, and say we have solved the electronic Schrödinger equation like at all of these points, and then we connect them by a smooth line, and that gives us a potential energy surface. That potential energy surface that has a minimum here, that is the equilibrium distance. Around that minimum, that potential energy surface looks pretty much harmonic. Yeah? So it looks like a quadratic function, so there is a harmonic region here. And then the depth of that potential energy surface up to the dissociation limit, that is called the dissociation energy. It is actually fairly misleading to call this a potential energy surface, because as you know, this is like the total energy of the molecule as it comes out of solving the electronic Schrödinger equation, and sure enough contains the kinetic energy of the electrons. So calling it a potential energy surface is a bit of a misnomer, but it is what everybody's doing. Okay, so that means if you stretch that molecule back like out of equilibrium, the energy rises, and that means there will be a restoring force that will want the molecule go back into equilibrium. And the classical model for that would of course be two masses that are connected by a spring. And every spring has a force constant K, and that spring constant K, that is what like pulls those masses either inwards or outwards, depending whether it's stretched or compressed. Now that is something that you can insert into the laws of classical mechanics, and by means of Newton's laws, then the force equals minus the first derivative of the potential as a function of the intermolecular distance, and by means of Newton's laws that equals the mass, the effective mass, times the second derivative of the internuclear distance with respect to time. Now for that molecule, you've seen the potential energy surface, and you saw that in the region of the minimum, it is pretty much harmonic. So that implies that we can make a Taylor expansion of that potential as a function of internuclear distance, and that contains like a term V0, that's just like the absolute value at the bottom of the well. Then there is the first derivative times r minus r bar, and r bar, that is the equilibrium distance, so that is the deviation from the equilibrium distance. And if we make that expansion at the equilibrium distance, then this point is 0 because the first derivative at the minimum is vanishing, and what you're left with is the second derivative of that potential energy at the equilibrium distance multiplied with the displacement squared. So now in our molecular model, then that second derivative of the potential energy with respect to the internuclear coordinate, that is the force constant K that we associate with that spring constant. And so that is very important. It's like the second derivative of the molecular energy of like the electronic energy you get out of the electronic Schrödinger equation that defines the force constant, the stiffness of the spring. And when you do quantum chemical calculations, so that tells you that is what you have to do. You have to calculate the second derivative of the energy, and in the practical courses on vibrational spectroscopy, of course, you have done that. Now, if we insert all of that then into Newton's laws, and we can drop this term V0 because it is a constant, and we might as well define the zero of energy to be just V0, then it is vanishing. Then you get Newton's differential equation, and which means that the second derivative of the internuclear distance with respect to time is minus the force constant divided by the effective mass times the displacement. So that is something that by looking at your old math lectures or by going through computer algebra programs, you can easily solve, and what you get then as a solution is a trajectory of the system, as I explained in the first lecture. So you get the internuclear distance as a function of time, and that is the equilibrium distance plus a harmonic motion. Yeah? So a sine and a cosine that depends on the initial conditions under which you get the vibrational motion going. So and that determines these constants of integration C1 and C2. But the important point is that the characteristic quantities that you have here is the vibrational frequency. So that is this stuff here that sits inside as the argument of the sine and cosine functions. And that is the vibrational frequency, which is 1/2 pi times the square root of the force constant divided by the reduced mass, the effective mass. And the effective mass, and that is important, equals the product of the two masses, Ma and Mb, divided by their sum. That comes out of that treatment fairly easily. So that basically defines harmonic motion in a classical system. And that is good. And of course, the effective mass then gives you a handle on the isotope shift. So when you see this is the expression for the vibrational frequency, and it contains a force constant that is simply a property of the molecule and a function of the strength of the molecular bond. And this is a reduced mass, and that obviously depends on the atomic masses. Now, as a chemist, you have the wonderful ability to change these masses to whatever isotopes are available. And so the vibrational frequency will change as you change these masses Ma and Mb towards Ma prime and Mb prime. And so if you ask yourself, how does the vibrational frequency change as a function of that change in masses, then you will find that the modified vibrational frequency nu prime equals nu times the ratio of the two reduced masses and the square root of which. Now you can insert that and you get this expression here, and if you take the example of making an isotope replacement we replace the natural isotope 16 oxygen by 18 oxygen, then you will find that you expect the vibrational frequency to go down by 5.7%. And so because the heavier nuclei have lower vibrational frequency. So, and that is actually pretty close to what you normally find, and that shows you that you can use these isotope substitutions to prove the nature of a molecular vibration. So if you do that change, like you replace 16 oxygen by 18 oxygen, and most of the time you know exactly where that 18 oxygen goes, and then your vibrational frequency changes in the experiment, then you have positively proven the involvement of oxygen in that molecular vibration. So that is cool. Now, one thing we have to talk about then is force constants, and when you talk about force constants, you have to talk about units. And I realize that the only people on the planet who know how to deal with units are physicists, and so if you have a question on that, you better go to your friends from physics because they know that stuff. In vibrational spectroscopy, the units are fairly strange. Now, taken face value, the second derivative of the potential energy with respect to nuclear coordinates, that is simply energy divided by area. So that is the type of dimensions that you have here. And of course you can express that as 10 to the minus 18 joules divided by angstrom squared, which happens to be 100 Newton per meter, which happens to be the definition of millidyne per angstrom. That certainly is not an SI unit, but that is the unit that vibrational spectroscopists use when they talk about force constants. So here's your conversion, it's millidyne per angstrom. And to get us oriented, I've listed here a few typical force constants for small molecules to tell you what bonds are stiff and what bonds are less stiff. For example, one of the strongest bonds in chemistry, the N2 molecule, has a force constant of 22.4 millidyne per angstrom. CO is a little lower, 18.6 millidyne per angstrom. O2 is considerably lower, because that's not a triple bond. These two are triply bonded. Then you have 11.4. For F2 you have 4.4, H2 5.2. So you get a feeling of what a strong bond is and what a less strong bond is. Yeah? So generally speaking, force constants become large if the bonds are strong. That is not quite the correct statement, because what is the strength of a bond is the dissociation energy, and that is of course not what is measured by the force constant. By the force constant is only measured the restoring force in a displacement from in the harmonic region, and so the force constant is measuring the stiffness of the bond. Yeah? You definitely have observed trends that force constants that are stiff tend to be associated with high dissociation energies, but they don't have to be. So you can have a potential that is like very narrow, very steep, but not very deep. Yeah? So it is not necessary that you have high dissociation energies associated with large force constants. As a rule of thumb, however, this is so. It is also not a rule of nature that bonds with a force constant have to be short. However, this is largely what is observed. So typically bonds with large force constants also tend to be short. So they tend to be strong and they tend to be short. So the force constant obviously is something that is like super important in chemistry. There is an empirical rule, stone-old empirical rule, that is still used a lot in chemistry, and that is exploring the relationship of the force constant with equilibrium distance. It's known as Badger's rule, and Badger's rule states that the force constant roughly is 1.86 times the inverse third power of the equilibrium distance minus a constant that depends on the nature of these atoms. And in his original paper from 1934, Badger has listed the value of these constants, Dij, depending on the nature of the atoms that are involved. Yeah? So for example, for HH, you have a constant of 0.05, and if you have the bond between a hydrogen atom and a third row atom, that constant would be 0.65. So that means if you have measured the force constant, you can deduce an intermolecular distance, or vice versa. If you have measured an intermolecular distance, like interatomic distance, you can get an estimate of the force constant. Both of these are possible. It is widely employed in chemistry. It is an empirical rule. Yeah? So it's not something that has been derived from like deep fundamental quantum mechanics. It is something that has been derived from experiment. So here is the relationship between force constants and bond strength, as I told you about. And generally speaking, you will see that as the force constant goes up, the dissociation energy goes up. But of course, that is a relationship that has significant scatter in it. So you will find quite a number of molecules here, like KCl or sodium chloride, that are pretty far off the straight line. You can justify the relationship between the force constant and the dissociation energy by looking at a Morse potential. So that is a Morse potential curve. It's like pretty much one of the simplest possible mathematical equations that give you the correct shape or quantitatively correct shape of a dissociating bond. So it has a minimum here, and then for infinite distance it goes to a constant. And so the Morse potential is one of the simplest expressions that qualitatively models the shape of a potential energy surface for a stretching bond. And that expression is the dissociation energy times 1 minus the exponential of a constant beta times the interatomic distance. Now if you take the second derivative of that, you will find that the second derivative, which equals the force constant, equals 2 times the dissociation energy times that constant beta. So that means if you study the Morse potential, you get a relationship between the force constant and the dissociation energy that is linear. So that qualitatively justifies the observed trends. But be aware that it is not quite universally so, and there is quite a scatter in the relationship between force constant and bond strength. So far we have then looked at a classical model of molecular harmonic vibration, and of course, as you know, molecules are not classical objects, so there is also quantum mechanics associated to it. And so if you want to proceed one step further, then you have to look at not the classical harmonic oscillator, but the quantum mechanical harmonic oscillator. And so what we have to look at are the vibrational states of a diatomic molecule. And so, as it was the case for electrons, it's the same for nuclei. You have to replace the trajectory, so r of t, by a nuclear wave function. And that nuclear wave function is the probability amplitude for finding the nuclei in a given nuclear configuration. Now, obviously what we have to solve now is the quantum mechanical equation, and the simplest case is a harmonic potential. So this is just simply a harmonic quadratic potential. Now if you solve that, that is something that is always chapter 2 in any quantum mechanics book, because the harmonic oscillator is one of the most important model systems in quantum mechanics. So the physics is deeply embedded into the harmonic oscillator. Now, if you solve that, you get the solutions of the Schrödinger equation, and for a harmonic potential, you will find that the eigenvalues of the harmonic oscillator are evenly spaced. And they're actually n plus 1/2 times h times nu. Yeah? So that is the vibrational energy, h times nu. Nu is the frequency of the harmonic oscillator. And n is then the vibrational quantum number. And n ranges from 0 to infinity. But interestingly, there is vibrational energy even for zero quanta. So even if n equals 0, there is an energy of 1/2 times h nu. That is something that is like a base level energy that every harmonic oscillator just has. Yeah, so there is energy in molecular vibrations, even in the vibrational ground state. That is very important. It's known as a zero-point energy. When you do thermochemistry of like reaction energies or transition state energies, the zero-point energy of the molecular vibrations is something that you definitely have to take into account. Yeah? And so these vibrational energy levels in the harmonic approximation are evenly spaced. Now in blue here are the vibrational wave functions of the harmonic oscillator. And so what you see here is that in the lowest vibrational state, that is simply a Gaussian curve, and the Gaussian curve has a maximum at 0. So that means that the highest probability of finding these nuclei is right at the equilibrium distance. So that is good, and that corresponds pretty much to your classical picture. And then there is a distribution of probabilities, and there is even probability lacking out of the boundaries of the potential. That is tunneling, nuclear tunneling. Now you see the higher vibrational states, the higher you go, the more the maximum of the probability distribution move towards the edges of the potential well here. And that is something that means that qualitatively that corresponds to the molecule like making larger and larger vibrations as you excite it into higher and higher vibrational states. So these are vibrational wave functions. So what I've plotted here are actually the squares of the nuclear wave functions. Yeah, so they are always positive. The nuclear wave functions, and you may not need to know that in much detail, but you will have heard that mathematically they're so-called Hermite polynomials. Yeah, so it's a Gaussian function multiplied by a Hermite polynomial, for those of you who are particularly interested. So this is very fundamental. So anything that involves the nuclei and nuclear motion is firmly rested onto the harmonic, quantum mechanical harmonic oscillator and its properties. The zero-point energy, the evenly spaced energy ladder, and the shape of the vibrational wave functions. Now, in reality, of course, motions are not harmonic. And so what you see here is a more realistic potential, and that looks a little bit like that Morse potential that I've shown you. That's a realistic potential for a molecule, and that is its harmonic approximation. So you see down here, close to where the vibrational ground state is, that parabola fits the actual potential pretty well. And then as you go higher in energy, that parabola is not such a fantastic match. And so what you see here is that as you go into higher and higher vibrational states, the actual vibrational level in an anharmonic oscillator is lower in energy. So these levels are no longer evenly spaced if you go to real potential, but they show some deviations from that. Now, that obviously has consequences. And one of the consequences is, of course, when you calculate a vibrational frequency, you calculate invariably harmonic frequencies. Yeah? So you calculate your frequencies as if the potential would be fully harmonic. Yeah? And of course, that is not what real frequency is, because real frequency is happening in enharmonic potentials. That means when you compare a calculated vibrational frequency to an experimentally measured frequency, there is an inherent error that you make that comes from neglecting the enharmonicity. So in principle, in the perfect world, if you have a molecule, the molecule has a vibrational frequency, and you would solve Schrödinger's equation exactly, you would not calculate the perfect vibrational experimentally observed frequency. Yeah? There is a deviation from it, and that deviation comes from the enharmonicity. So that means any comparison that you make between calculated frequency and experimental frequency will ultimately involve some error that you make by the neglect of enharmonicity. Yeah? The second feature that you have here is obviously due to the presence of the zero-point vibrational energy. What you're measuring is not the dissociation energy dE, but what you're actually measuring is the energy that is known as d0, and that is dE minus h nu, so the vibrational energy. For diatomic molecules, it has been worked out that a useful expression for the enharmonic oscillator is h nu times n plus 1/2. That is the harmonic oscillator energy, and then minus an enharmonicity constant xe times h nu times n plus 1/2 squared. So that is the enharmonic correction, and you will have many diatomic molecules for which that has been determined experimentally. There is a groundbreaking book by Herzberg that lists a few hundred of those constants. Yeah? So this is like a slight disclaimer that you have to pay attention to enharmonicity effects. Or at least you have to be aware that they exist, and don't expect your calculated frequencies to be perfectly on top of experiment. If they are, it's a sign that there is an error compensation in your electronic structure. This actually, when you calculate vibrational frequencies with, say, the BB86 functionals, then the calculated frequency very often are very close to the experimental ones. That is error compensation, because the BB86 frequencies tend to be a bit too large when you compare to true harmonic frequencies. So, with that, we have to go to polyatomic molecules. So obviously, our molecules are not diatomics, they're polyatomics, and that means you have more complicated molecular vibrations. In the diatomic molecule, you have exactly one frequency and one vibrational mode, which is the stretching mode. Now, in polyatomic molecules, you have different forms of movement. So you have stretches, you have bends, and you have torsions. More complicated motions can usually be expressed as the linear combination of stretches, bends, and torsions. And I'm sure that all of you know that for an N-atomic molecules, you have 3n-6 degrees of freedom, or 3n-5 if the molecules is linear. I will from now on just say 3n-6 in order to not having to talk awkwardly, but you all are aware that it's 3n-5 if the molecule is linear, yeah? Okay, and that means for an N-atomic molecules you have these 3n-6 vibrational frequencies, and also you have 3n-6 vibrational modes, and these are the normal modes Qi. And in the harmonic approximation, that means you have 3n-6 harmonic oscillators, yeah, that are uncoupled. Yeah? So you have 3n-6 harmonic oscillators that are uncoupled. That means you have to think that graph that I've shown you here, you have to think this in 3n-6 dimensions. That is a bit hard, but so you can say you have, like, say, a set of cards, 3n-6 cards, and each of these cards contain a harmonic oscillator with the harmonic oscillator wave functions, the harmonic oscillator frequencies, and the harmonic oscillator energy ladder. Yeah? So in general, normal modes are a little bit like molecular orbitals in that they extend over all of the molecule. In very many papers you find very simplistic discussions of vibrational frequencies where people think, oh, you see, I have observed this and that CO stretch, and that means that whatever I have done to the molecule happens right in the region of that CO bond. That in general is not a valid conclusion because these modes are delocalized all over the molecule. And that means you can observe an effect on a CO bond at this point when something happens at the molecule very far away. So be careful if you don't jump to conclusions. If you want to do it properly, you really have to analyze the normal mode structure of your molecule. Yeah? So as I said, in general, you can express these normal modes as linear combinations of these primitive stretches, bends, and torsions. Just to mention briefly, why is it 3n-6? And the 3n-6 comes from the fact that if you translate the molecule as a whole, or you rotate the molecule as a whole, there is no restoring force, right? Because you don't change any of the bonds in the molecule. And so these are forms of molecular movements that are associated with force constant 0. Yeah, so the translation in x direction, in y direction, and in z direction, as well as the rotations, the three possible molecular rotations around x, y, and z are not vibrational motions. There is also quantum mechanics associated with translational and rotational motions, but we're not getting into that. That is something that gas phase spectroscopists have to worry about, but not us. And so you see also why 3n-5 in the linear molecule, because if you have a linear molecule, the rotation around the bond axis, that is not a rotation. Okay, so these are things that are 0. If you have a quantum chemistry program, like checking that these frequencies are really 0 is a good idea. Most programs will project these motions out before they determine the vibrational frequencies. Some may not, and then like the deviation from 0 is a measure of the quality of the calculation, because ultimately any numerical frequency or like frequency calculation in general will involve a little bit of numerical noise. The numerical noise is worse for the very low frequencies, and it is the worst for those frequencies that should be 0. If you use Orca projects these translations and rotations out, so you get exactly 0 for these 6 frequencies. So now let's look at a few normal modes, and I think like the normal modes that everybody has to look at some point in chemistry are the normal coordinates of water. So you have 3 atomic molecules, you have 2 hydrogens here and an oxygen there. 3n minus 6 equals 3, so there are 3 normal modes in water, and the lowest energy one is a bending coordinate that is totally symmetric and is found at 1595 wave numbers. So, as you see from these arrow diagrams, obviously the molecular vibrations, they also transform under the irreducible representations of the point group. So, one more reason to study group theory is you can not only classify molecular orbitals, you can not only classify many electron states, but you can also classify molecular vibrations under the irreducible representations of the point group. So this is a vibration of A1 symmetry. It's totally symmetric, it's a bending mode. Now the second one is a symmetric stretch, where both of these OH bonds symmetrically stretch. It's found at 3650 wave numbers, and there is an asymmetric stretch that is found at 3756 wave numbers, where these bonds stretch out of phase. This one is also totally symmetric, whereas the asymmetric stretch transforms under B1. Yeah? And there are characteristic IR and Raman spectra, of course, of water, and so you see here the very large asymmetric stretch. Fine. Second example, CO2. These are the normal coordinates of CO2. There are 4 of them because it's a linear molecule, and you have an antisymmetric stretch that's highest in energy, 2350 wave numbers, that transforms as sigma grade. Then a symmetric stretch where the CO bonds stretch in phase, and then there are 2 out-of-plane and in-plane bending modes that are at the same energy because there is symmetry, so that is a doubly degenerate vibration. Obviously, it quickly gets pretty complicated, and the forms of the normal modes are complicated. But all of you in chemistry have learned that there are characteristic vibrations of characteristic groups, and they're summarized in tables like this. You find that in every organic chemistry textbook, where you will know that, say, CH bonds in alkanes typically lead to IR absorptions in the region of 2960 to 2850 wave numbers. CO single bond like is somewhere between 1000 and 1300 wave numbers. The CO double bond is on the order, is in the range of 1700 wave numbers, and so on and so forth. And these are super useful to get a first orientation on where you expect molecular vibration to come from. But of course, any of these vibrations is affected to what that functional group is actually bound to. And if you want to do it properly, then you have to do a normal coordinate analysis. And in general, that works like that. So you will have to have a force constant matrix that is called the Hessian matrix. And the Hessian matrix consists of the second derivative of the energy with respect to a pair of nuclear coordinates. So for example, the x coordinate of atom A and the y coordinate of atom B. So that is a force constant matrix. It is of dimension 3n times 3n. Yeah? And then if you diagonalize it, it should have 60 eigenvalues that corresponds to the translation and the rotation. So now what you have to do in order to go from your precious Hessian matrix to vibrational frequency is to first scale the Hessian with the atomic masses. So for the, you go to the mass weighted Hessian, and if you want to express this in millidyne per angstroms, if your force constants are in atomic units, your unit conversion comes out to that being multiplied by 15.57 times the force of the Hessian matrix element divided by the square root of the product of the masses. Then you diagonalize that, and diagonalizing that matrix, that gives you the eigenvalues of the mass-weighted Hessian and the eigenvectors of the mass-weighted Hessian. And from those, you calculate the vibrational frequency. And the vibrational frequency in wave numbers, if your mass-weighted Hessian is in millidyne per angstrom, is 1302.78 times square root of the eigenvalue. So you see that is you don't even want to know how many constants go in here before you arrive at 1302.78, but just take it for granted that's the easiest. Yeah? And then the actual normal mode comes from the eigenvector of the mass-weighted Hessian by applying the inverse square root of the mass matrix. Fair enough, every program does that for you, and you will know how to use a visualization program to look then at the shapes of these molecular vibrations. This is cool if you have an accurate force field, and an accurate force field for a larger molecule invariably comes from a quantum chemical calculation of some kind. Yeah? The errors relative to the perfect harmonic frequencies, as I told you, just reflect the shortcomings of the theoretical methodology, and they're hard to fix, right? And it's because we have solved the Schrödinger equation as good as we can, but we can't solve it perfectly, so there are invariably errors in these frequencies. And the second, of course, is the limitations by having harmonic frequencies compared to enharmonic frequencies that you observe in reality. Now, if you are hardcore vibrational spectroscopists, they don't like that type of thing. Then they say, fine, it's okay to do a calculation, but that is, I mean, what separates like the boys from the men is like to do this by hand. Yeah? And so what they do is then they set up a model for the molecule at hand. In this case, say it's like a manganese with an oxo group and a hydroxyl group. And they choose the relevant internal coordinates SI. These are the primitive, like stretches, bends, and torsions. Then they guess a force constant matrix. They include the geometry, that is so-called FG matrix approach, that you will find in the old books on vibrational spectroscopy, solve the eigenvalue problem, and then they get frequency and normal modes. Now, what happens here, of course, is that each of those internal coordinates, stretches, bend, and torsions that are set up in that force field comes with an empirical parameter, and that empirical parameter, that is the force constant. Yeah? And so the force constant is an empirical parameter that goes in here, and that is then fitted to experiment. So here you have a least square fit to the experiment. What you get out are the force constants. The downside of this is, so this is cool, and you have total control over what you're doing, but of course it depends a little bit on the investigator's intuition of how to properly set up such a force field. And you will then, unfortunately, if you study it mathematically, you will come to the conclusion that there is an infinite number of equivalent force fields that all lead to the same vibrational frequencies. So, and they will have different number and different nature of force constants. And that means that the value of the force constants that you get out of the fit is not unique. And that in turn means that a force constant isn't really a physical observable. As much as we like these force constants and we like to think that they're uniquely defined, as a matter of fact, they're not uniquely defined. Yeah, so there is an infinite number of force fields that all lead to the same vibrational frequencies. And at the end of the day, the only observable are the vibrational frequencies. Yeah? Now, this is almost a forgotten art. There are very few groups that still go through the process of doing a normal coordinate analysis by hand, but I wanted to at least mention that it's possible, and if you want to have like full control over what you're doing and not just blindly trust the quantum chemistry program, this is what you have to do. Okay, now we go to vibrational intensities. I think now we have talked about the vibrational frequencies, and now we talk about the vibrational intensities. And before going into that, I wanted to remind you again what the three experiments are that we're talking about. Now what we have here is the potential energy surface of the electronic ground state, and it has the ground state vibrational energy levels in here, and associated with it the ground state vibrational wave functions. Yeah, so far so good. And when you do an IR excitation, you simply do transitions from the vibrational ground state in the electronic ground state to a vibrational excited state in the electronic ground state. Now, if you go to the excited state, of course you have a potential energy of the excited state that looks different than the potential energy of the ground state, and it has a set of vibrational frequencies that are different than the vibrational frequencies from the ground state. That makes sense, because once you have excited the molecule, all of the chemical bonds in the molecule change. You have heard Felix Tukcek yesterday. He had this wonderful molybdenum nitride complex that had molybdenum end stretching frequency of 980 wave numbers in the ground state, and it was, remind me, 870 or something in the excited state. Yeah, so these vibrational frequencies are typically different than they are in the ground state. Okay, so far so good. Now we have the IR experiment is clear. Everything happens just in the electronic ground state. Now your photon in the Raman experiment is much higher in energy and quite typically not enough to actually reach the electronically excited states. So here you have something that is a bit weird, and what people are talking about, although I don't think it is a very good term, they say you get an excitation of one photon to a virtual level followed by emission of a second photon that goes into the vibrational excited state of the electronic ground state. So you can think about, you start in the vibrational ground state of the electronic ground state. There is a virtual absorption of a photon followed by real emission of a photon into the vibrational excited state of the electronic ground state. That is kind of imperfectly using language to describe some quantum mechanical equations. We will get back to that in a moment. Now, the resonance Raman experiment, that is actually easier to understand, because in the actual resonance Raman experiment, you do an excitation from the vibrational ground state of the electronic ground state onto the excited state potential energy surface. Then something happens here on the potential energy surface that I talk about in a minute, followed by emission of a photon into the vibrationally excited state of the electronic ground state. So both in the Raman and the resonance Raman process, then the actual energy difference that you observe between the exciting photon and the detected photon, yeah, that corresponds to vibrational energy. That is the important thing. Now, of course, you can have more complicated excitations like that, and unfortunately nature is so mean to show you all of these things. Yeah, that is, normally you would say it's complicated enough. I have these 3n-6 harmonic oscillators, and I get my excitations from the vibrational ground state to the first vibrational excited state in all of them. But of course you can have more complicated excitations like that. So that's why vibrational spectroscopists talk of fundamentals when they observe an excitation from the vibrational ground state of a given normal mode to the first vibrational excited state. So this is simply this excitation from the vibrational ground state to the first vibrationally excited state. They talk about a hot band if you have the opposite. If you observe an excitation from a vibrationally excited state into the second vibrationally excited state or back to the ground state. You talk about overtones when there are multiple quanta excited in a given vibration. So if you go, say, from the vibrational ground state to the second or third or fourth or whatever vibrationally excited state. These are in principle forbidden, but they can gain intensity through various intensity borrowing mechanism. And you talk about a combination band when you observe excitations where two molecular vibrations are being excited at the same time. So if you have, say, two normal modes, Q1 and Q2, and you simultaneously excite an excitation from the vibrational ground state to the vibrational excited state here, that's a combination band. All of these things happen. We are very used, most of the time we are all very used to look at a vibrational spectrum and attribute everything just to fundamentals. But unfortunately, not everything is just fundamentals. And you've seen, for example, in Felix Dubček's absorption spectrum that there was a nice progression of several quanta of a given vibrational mode. And you can have that in IR Raman and resonance Raman spectra as well. Here's a nice example that I think I borrowed from Raman Transitions. That is a coordination compound, a relatively simple nickel complex, and its resonance Raman spectra are very rich. And here, for example, what they have assigned is a long vibrational progression up to 6 quanta in one vibration, that is totally symmetric stretching vibration. And here is the second progression of like 5 quanta, that is a combination band. So that is a combination of the totally symmetric stretching vibration with the second vibration U2. So these things exist, and if you want to understand these spectra, you have to be aware that those overtone and combination bands can exist. Ultimately, without the help of theory, you're not in a happy man's land when you analyze vibrational spectra. To simulate modern EPR spectroscopy without some input of theory, it is almost impossible to really analyze these spectra to the end. Yeah? Now we talk about the physical principles that govern the intensity of the vibrational transition. And in IR spectroscopy, that is relatively easy to understand. So let's look at, say, our water molecule here, and it has a dipole moment. And the dipole moment changes as a function of geometry. Yeah? So when you do distort the molecules during the vibration, the dipole moment changes. And as the dipole moment is changing, then you can have that. What happens is that the dipole moment fluctuates as a function of time. That is a classical physics picture. And so what you have then is an oscillating dipole. And an oscillating dipole is an antenna. And so basically what happens here is that the oscillating dipole acts as an antenna for the IR photon. And if the IR photon has the same frequency as the oscillation of your dipole moment, then there is resonance. So that means your selection rule is that you only pick up an IR photon, so you only have an IR loud transition if there is a change of dipole moment during the course of the vibration. That happens along non-totally symmetric modes or ungerade vibrations, explaining that selection rule that you're all familiar with. Yeah? And so the intensity then is proportional to the first derivative of the dipole moment with respect to the normal mode. Yeah? So that is your selection rule, and you square that, and that is then proportional to the intensity of the IR transition. Now the Raman transition is a little harder to understand because it's a two-photon process, as I explained to you, and then it is difficult for humans to come up with words that correctly describe the quantum mechanical equations. I will try. So again, we start from our dipole moment, and then we put in an electric field. And then an electric field will change that dipole moment, which means that there is an induced dipole moment, that comes on top of the original dipole moment. And that induced dipole moment is proportional to the strength of the electric field. And what is in between there is something that is connected to the molecular electronic structure, and that is called the polarizability tensor. Yeah, so there is an induced dipole moment that comes from an electric field, and the proportionality is the polarizability tensor. Now, a radiation field has an electric field, so that means if you bath the molecule in a radiation field, there is an induced dipole moment. And you can think of basically the first photon that we talked about as creating such an induced dipole. Now, if the molecule vibrates, then this induced dipole moment will also oscillate. And so there will be resonance with the photon if there is a change of the induced dipole moment in the course of molecular vibration. Yeah? And then the second photon is emitted at the vibrational energy. Now, if you do that mathematically, obviously what we have to do is to calculate the polarizability tensor. Now, the polarizability tensor in general is given by an infinite sum over states. So here we have the perturbation theory again that we talked about in the lecture of effective Hamiltonians. Now, the Raman transition is proportional to the first derivative of the polarizability tensor with respect to a normal mode squared. So basically that is what it is. You have an induced dipole moment, and the induced dipole moment that is being picked up by the radiation. Now, of course, if you don't have a static electric field, but you have an oscillating electric field, you're not talking about the static polarizability here, but what you have to look at is the frequency-dependent polarizability. And there's a famous equation coming from the greatest of the greatest, that is the Heisenberg equation. And then it tells you that the frequency-dependent polarizability, and that is really the quantity that we have to look at, has two terms. And one of those terms, so it has a dipole moment coupling of the ground state to the excited state, obviously in both of these terms, but in the denominator you have two terms, a resonant term, so here's an excitation energy, that is a photon energy, and that is a phenomenological parameter that describes line width. So the difference here is that you have minus the excitation energy minus the photon energy here, and you have the excitation energy plus the photon energy here. So now what will happen if the photon energy is equal to an excitation energy, this term will blow up. It will blow up to infinity, unless you have this like phenomenological modification here. Now that means, that explains to you the resonance Raman effect. Yeah? So the resonance Raman effect arises if the photon energy equals an excitation energy, and then you get a peak, a big spike in the frequency-dependent polarizability. And as you have that peak in the frequency-dependent polarizability, the intensity of the Raman peak will go up by many orders of magnitude, and this is why resonance Raman spectroscopy is selective. Yeah, so when you excite into the chromophore, you get Raman peaks that are orders of magnitude enhanced relative to the standard Raman peak, where that photon energy is far from resonance. And if it's far from resonance, you might as well replace this equation by that equation. Yeah? But the resonance Raman effect, then this infinite sum over states will be dominated obviously by the one state, by the one electronically excited state that is in resonance with the photon energy. Yeah? And so if you look at that, you can also now calculate it, and here we do something that I also talked about in the lecture of effective Hamiltonians. You replace that infinite sum over excited states by a molecular derivative. And when you do that, you will find that there are two contributions to the resonance Raman intensity. There's a smaller term that involves simply the first derivative of the dipole moment coupling matrix elements with respect to the normal modes, and a larger term, and that involves something that is interesting, that is simply the excitation, the derivative of the excitation energy with respect to the normal mode. So there is a transition energy gradient. And now the transition energy gradient can only be non-zero for totally symmetric modes, and that is because the excitation energy, the Hamiltonian, is totally symmetric. Now that is very important because it tells you one thing. It tells you that in order to have resonance Raman intensity, if you don't talk about this term here, what you have to have is an excited state displacement. That is the important point. So here you have the ground state potential energy surface. Here you have the excited state potential energy surface. And you can only have resonance Raman intensity if the minimum in the excited state is at a different place than in the ground state. If everything before was gibberish to you, then remember this. Resonance Raman spectroscopy is measuring the distortion of the molecule in the excited state relative to the ground state, and there is a distortion parameter delta. So that excited state distortion really is what governs the resonance Raman intensity. Yeah? And that means that these distortions only occur along totally symmetric modes, unless, of course, you excite into an orbitally degenerate excited state, which is a special case. In general, it means it only occurs along totally symmetric modes, and that means resonance Raman spectroscopy is a fantastic tool to observe these totally symmetric stretching vibrations that have no IR intensity. That is the way it is. Now, if you have to calculate the resonance Raman spectrum based on a picture like that, it becomes very complicated due to the fact that you have a 3n-6 dimensional problem. There is a slightly obscure but very elegant way to do that, that is what ORCA is based on, where you can calculate the resonance Raman spectra without solving a 3n-6 dimensional problem, where you basically can break down the problem of 3n-6 dimensional Frank Condon factors to one dimension, and that is so-called Heller theory. And the Heller theory creates a little bit of a different physical picture of the resonance Raman process. It all, at the end of the day, is mathematically equivalent to each other, but I want to try that out on you. So let's pretend you start in the vibrational ground state of the electronic ground state, and that is such a Gaussian wave packet. Now you absorb at time equals 0 a photon, and you adiabatically transfer that Gaussian wave packet onto the excited state, where it is no longer an eigenstate of the vibrational Hamiltonian. That means what will happen is that the system becomes time dependent, and that Gaussian wave packet will start to have a dynamics here on the potential energy surface of the excited state, and eventually will drop down and emit. And what the Heller theory is telling you, that what you have to calculate then is a kind of time autocorrelation function of that Gaussian wave packet in the initial and final states. It is a bit involved, but in the computer it's easily implemented, and it's easily implemented for multi-dimensional systems. The sheer fact that ORCA can calculate resonance Raman spectra for you, and it only takes you a few seconds, is because this has been carefully implemented. It has been carefully implemented and developed by Taras Petrenko. And it is a very powerful tool. I mean, for the longest time, it was not possible to calculate resonance Raman spectra for more than, say 3 or 4 or 5 atoms. And even that was expensive. Now, that impossible problem has now been solved, and you can calculate resonance Raman spectra for molecules with a few hundred atoms. And it's no problem because of the blessings of Heller theory. I want to illustrate that to you with a toy system in order to make it slightly less obscure. Yeah, so I realize that this is theoretically a bit hard, but so now I want to bring it back to something that is chemically tangible. So we look at a toy system. Our toy system is a copper complex. So let's assume there's a copper complex. Here is the tridentate ligand with 3 nitrogen donors. And here we have, say, chloride ligand. It's an approximately square planar complex, so we kind of understand the electronic structure of it. You have highest in energy, the molecular orbitals that are based on the metal d orbitals. You can see them here. They're essentially non-bonding XZ, YZ, XY, and Z squared orbitals. And the singly occupied molecular orbital, you have a copper 2 complex that is the sigma anti-bonding orbital that is quite a bit energetically separated from the rest of the d block, and it contains sigma anti-bonding interaction between the coppers and the ligands, with the base of the dx squared minus y squared orbital. A little lower in orbital energy are then the chlorine p orbitals, and even lower in energy are then the sigma orbitals of the nitrogen ligands that you see here. So that is, I think, an easy to grasp electronic structure, and that's got to be reflected in the absorption spectra. Now, if you look at the absorption spectra, then you will find a low energy peak somewhere around, say, 15 to 20,000 wave numbers, yeah, which is like between, say, 5 and 700 nanometers, and it is low energy, and that will be DD transitions. Yeah, if you look at it carefully, then you will see there are obviously up to 4 DD transitions. And a good way to find these DD transitions, if you don't see them in absorption, is to go to the circular dichroism spectra. And the circular dichroism spectra have the property, we will not analyze it here, that DD transitions tend to be very intense in the circular dichroism spectrum, whereas they tend to be weak, as Felix has explained to you in the absorption spectrum. Then there is a gap where nothing happens, and to higher energy you have charge transfer transitions. And so the first charge transfer transitions that you see are from the chlorine p orbitals into the SOMO. Yeah? And a nice way to look at that is to look at difference densities. So you can calculate the difference in electron density between the ground state and the excited state. And so what you will see here for the DD transitions is that the difference density, there is not much density transfer, and so actually red is positive, is where electron density goes up, and yellow is negative, where electron density goes down, yeah, between the ground state and the excited state. There is not much change in electron density because that is a transition that is pretty localized on the copper. Whereas when you look here at the charge transfer peaks, you will find that there is a charge transfer peaks of pi symmetry and of pi nature, and you see that nicely that the region where electron density is depleted is here in the pi orbitals of the chlorine, and where electron density is gained is here in the region of the copper. Yeah, and so you can look at it here, and so you have to higher energy an intense sigma charge transfer, and to lower energy a less intense pi charge transfer. That is fairly typical for transition metal complexes. So here you have a very nice, textbook, spectrum of a transition metal complex, lower energy DD transitions, mostly localized at the metal ion, weak absorption, strong CD signal, actually also strong MCD signal, where there is the same. Then you have a lower energy, lower intensity pi charge transfer, higher energy, higher intensity sigma charge transfer transition. So that is nice. And I want to parenthetically make a remark, because I think there often is a lot of confusion around that in discussing optical spectra. Now, what governs the intensity of an absorption band is not the difference in dipole moments, but is the transition density. So it's a transition dipole moment. Now, and you see, and you plot the transition, so let's assume, and I think that is a good approximation for that molecule, that we can associate these transitions really with the excitation of an electron from one orbital to the other. Yeah? Then the difference in total electron density is simply the square of the acceptor orbital minus the square of the donor orbital. If all of the other orbitals don't change, which is an approximation, but I think that's a good way to think about it. So, and that gives you these different densities that I've been talking about. Now, the transition density itself is the product of the acceptor and the donor orbital. And you see the transition densities plotted here, and they look fairly different, like from the difference density. Now, you can have a molecule that has no dipole moment whatsoever, but has strong absorption bands, and that is because the product of the donor and acceptor orbitals, they have a nice dipole moment. Yeah, so you will see here that in the DD transition, that product is very small, and it has more of a quadrupolar shape. That is why these DD transitions are quadrupole allowed, but electric dipole forbidden. Whereas you can see here in the charge transfer region, you have a very nice dipole moment that points along the metal ligand bond. That's why you have nicely strong, intense charge transfer transitions and very weak DD transitions. So yeah, that is the bottom line here. So now in terms of resonance Raman, now you take a laser and you excite into your absorption bands. So you excite into your DD transition here and you see essentially nothing. And that is very characteristic. In DD transitions, you normally expect only very weak resonance Raman spectra. And the reason for that is that, as I told you, what you have to have is an excited state displacement. And in order to have an excited state displacement, the bonding must change. Yeah? So the nature of the chemical bond must be different in the excited state than it is in the ground state. Now for DD transitions, that is hardly the case. Yeah? So like a DD excitation does not change the nature of the bond between the metal and the ligand in a major way. That means there is very little excited state distortion, and that means there is very little resonance Raman intensity. Now on the other hand, you see if you excite here into these chlorine charge transfer bands, what you will see is strong resonance Raman signals. And these strong resonance Raman signals, they are dominated by one peak here. And that one peak, that is a copper-chlorine stretching vibration, and that makes sense, yeah? Because if you transfer an electron from a copper-chlorine bonding orbital in a copper-chlorine anti-bonding orbital, you greatly weaken the bond, yeah? And that means the bond gets longer in the excited state. And that, on the other hand, means you get a strong peak in the resonance Raman spectrum that corresponds to the metal ligand stretching. And that is an illustration of how resonance Raman spectroscopy works in general. It lets you look directly into the nature of the bonding. That's why it is so incredibly cool to do resonance Raman spectroscopy. Not only to fingerprint, because you can get such a nice detailed insight into the nature of the chemical bond. And so you can also see that in those potential energy surfaces. That is like harping on the same subject here. Now, if we study the potential energy surface of the system along the copper-chlorine bond, yeah, which is dominating the stretching vibrational normal mode. So you will see that there is a certain minimum here, which happens to be around 2.3 angstroms, and these are all of the D2D excited states. Yeah? And so you see there is essentially no distortion here along the copper-chlorine bond when you excite to the DD excited states. Yeah? And so here you have the absorption spectrum. So this is like the total energy. So these are all many particle states. And you can lay the absorption spectrum 90 degrees tilted on top of that. And so you see that along the DD excited states, a very weak absorption, very weak resonance Raman, because very little excited state distortion. Now you see here, when you excite into these copper-chlorine LMCT excitations, there is no minimum here close to where the minimum was. Actually, I don't even know where the minimum exactly is. So in this case, it is slightly flawed because these things look dissociative where they will not be. That is a shortcoming of the theoretical method used here, but like the important point is there is no minimum here in the Frank-Condon region. Yeah? And that means strong absorption band, long progressions, broad absorption band, and big resonance Raman intensity. So, with all of this, basically, and I think this will be my summarizing slide for the talk, you can use vibrational spectroscopy and in particular resonance Raman spectroscopy, to like fingerprint vibrations. You can use them to assign electronic transitions. You can use them to obtain a whole lot of insight into metal ligand bonding. And in order to do that, what you have to do is to be able to calculate the resonance Raman spectra. And what you actually do when you calculate resonance Raman spectra is to calculate these displacements. And these displacements, as I've shown you, you can calculate from excited state gradients. So all you have to have is the first derivative of the excitation energy with respect to the normal modes. That is something that in quantum chemistry is absolutely approachable, and in ORCA it is implemented in an efficient way for time-dependent DFT. Of course, we would love to have it for better methods, yeah? But that is incredibly efficient. It gives you all of the excited state displacements from a single gradient calculation. And then there is, once you have those excited state displacements, you can simulate the resonance Raman spectrum. So what was achieved with that development is the following. So remember how the spin Hamiltonian is the link between the electronic structure and the EPR spectrum. And it is a meeting point between theory and experiment. Yeah, so you can get the spin Hamiltonian parameters from fitting to experiment, and at the same time you can calculate them from quantum chemistry. Now, the way that we have done resonance Raman spectroscopy in ORCA lets you do the exact same thing with resonance Raman spectroscopy. You can calculate these excited state displacements from quantum chemistry. You get them like as a nice table, and then in the second step you can calculate the spectrum that you can compare to experiment. That also means you can calculate some displacements and take them as initial guesses for fitting to experiment. Yeah? So basically these excited state displacements take the exact role that the spin Hamiltonian parameters take. That all is implemented in the ORCA other program. That is an add-on to the ORCA program. Now that is incredibly powerful, and those of you who want to toy around with it, you can have so much fun with that. And if you have a tough problem to solve, you can really start to use this methodology in order to get a whole lot of insight into resonance Raman spectroscopy. Okay? I think this is all that I had to tell you for now. So what we have seen in this lecture is that force constant measures the stiffness of internal molecular motion, stretches, bend, and torsions. That normal modes and vibrational frequencies describe the eigenvibrations or distortions of the molecule, and they depend on the force constants that are actually different for each electronic state and the masses of the atoms, as well as molecular geometry. You can use then isotope shifts to identify the nature of these vibrations, and if you want to have detailed insight, you have to perform normal coordinate analysis. Now, vibrational intensities in the IR spectrum are dominated by the change of dipole moment in the normal vibrations. Raman intensities depend on the change of polarizability, and resonance Raman spectroscopy measure the distortion of the molecule in the electronically excited state. So this is another toolbox that you have available in order to characterize molecules. And I think together with all of the other spectroscopic methods that you have heard about in the school, this gives you a super powerful toolbox to characterize all kinds of molecules, be they stable molecules or be they reaction intermediates. I hope that this was fun. The last lecture that you will hear this morning will be given by Sheng-Fai Yi then on reactivity. And this afternoon you have more time to play with practicals.